Titan is lying to us, not passively, not accidentally. There is something almost deliberate in the way this moon presents itself to the universe, like a stage set constructed with surgical precision, designed to trigger every instinct you have for recognition, for familiarity, for the feeling of home. From a distance, it looks like Earth. Not vaguely, not metaphorically. It has rivers, lakes, coastlines, rain, clouds, seasons, and a thick amber atmosphere that wraps around it like a warm blanket on a cold night. If you squinted at the right photograph, the right angle, the right filter, you could genuinely mistake it for a satellite image of somewhere in northern Canada or coastal Scandinavia. NASA scientists have said exactly that, on the record, in peer-reviewed papers, in press conferences, and that resemblance is the trap. Because Titan isn't Earth. Titan is a freezing, toxic mockery of Earth. A world that studied our planet's blueprints, copied every architectural feature it could find, and then filled the entire structure with something fundamentally, irrevocably wrong. It is the most Earth-like object in the solar system. It is also one of the most hostile. Those two facts are not in tension. They are the same fact seen from different angles. Titan orbits Saturn at roughly 1.2 billion kilometers from the Sun. That is 10 times farther than the distance between Earth and our star. At that distance, the Sun is not a source of warmth. It is not even really a source of light. It is a dim pale point in an orange sky, barely brighter than a full moon on a clear night here. If you were standing on Titan's surface at noon on the longest day of its year, you would receive roughly 1/100th of the solar energy that reaches Earth. The solar panels that power most of our Mars rovers would be virtually useless there. The warmth that Earth's surface takes for granted, the basic thermal energy that keeps liquid water stable, that drives weather, that makes biology possible as we know it, on Titan, all of that is simply absent. Temperatures at the surface hover around negative 179 degrees Celsius. Let that number sit for a moment. That is cold enough to make steel brittle, cold enough to shatter certain metals like glass if you strike them, cold enough to turn methane, the same gas you'd smell near a leaking stove burner, a gas we treat as a mundane industrial chemical, into a liquid. And it is that liquid methane, not water, that fills Titan's lakes and rivers and seas. When the Cassini spacecraft arrived at the Saturn system in 2004, it carried a passenger, a small probe called Huygens, built by the European Space Agency, roughly the size of a large automobile tire, packed with instruments, and designed to do one thing: fall. On January 14, 2005, Huygens detached from Cassini and plunged toward Titan's surface. It took 2.5 hours to descend through the atmosphere, 2.5 hours of falling, recording, transmitting, surviving the cold and pressure and alien chemistry of a world no human instrument had ever touched. What it saw on the way down and what it found when it hit the ground changed how we think about moons, planets, and what it actually means for a world to look familiar. The atmosphere hit first. Titan's atmosphere is approximately 1.5 times thicker than Earth's at sea level. It creates a surface pressure of about 1.5 atmospheres, significantly higher than what we breathe. And Titan is the only moon in the entire solar system, out of more than 200 known moons orbiting all the planets combined, that has a substantial atmosphere at all. Every other moon is either airless rock or something so thin and transient it barely qualifies as atmospheric. Titan alone has a real sky, a real weather system, a real hydrological cycle. The atmosphere is mostly nitrogen, just like ours, around 95% nitrogen in fact. On paper, that sounds almost comforting. We breathe nitrogen. Our bodies are built partly from nitrogen. It is the inert, abundant background gas of terrestrial life. On Titan, that similarity means nothing. It is scenery. It is set dressing. The remaining 5% is where Titan reveals itself. That fraction is a cocktail of methane and hydrogen, laced with trace amounts of dozens of organic compounds. Ethane, acetylene, benzene, propylene, that react constantly with ultraviolet light from the distant sun to produce a permanent planet-wide orange smog. Tholins. Scientists call them tholins from the Greek word for muddy because nobody had a better name for molecules this complex, this varied, this stubbornly difficult to categorize. They coat everything. They drift down from the upper atmosphere in a slow, continuous drizzle of chemical snow, building up on the surface over millions of years, accumulating in the dunes, dissolving in the methane rain, being carried down rivers and deposited in seas. The entire surface of Titan is plastered in these organic molecules, some of the most complex abiotic chemistry anywhere in the solar system. The smog is so thick that sunlight barely reaches the surface at all. If you were standing on Titan at local noon, at the point of maximum solar elevation, the ambient light would be roughly 1,000 times dimmer than a bright, sunny afternoon on Earth. Not dark exactly. You would see your hands in front of you. You would see the ground beneath your feet. But the sky would be a uniform, oppressive orange-brown haze, and the sun would not be visible. You would not cast a shadow. You would be standing in something closer to the light level of deep twilight, the last minutes before full dark on a cloudy evening. Except it would never get brighter, and it would never get darker, and it would stay that color forever. Huygens recorded sound during its descent, not instrument noise, not radio static, wind. Actual wind buffeting the probe as it dropped through successive layers of haze. You can listen to recordings of that descent online. Huygens converted its accelerometer data into audio, and the result is a soft, irregular buffeting sound, like a microphone held out a car window on a highway. Titan has weather, real weather. It has a hydrological cycle so complete, so structurally identical to Earth's water cycle, that the same vocabulary applies to both, word for word. Methane evaporates from the surface, rises through the atmosphere, condenses into clouds at high altitudes, and falls back down as rain. The rain carves channels into the ground, feeds rivers, and those rivers carry their load of dissolved hydrocarbons downslope into lakes and seas that sit in basins near the poles. Ligeia Mare, one of the 3 major seas near Titan's North Pole, covers roughly 126,000 square kilometers, larger than Lake Superior, the largest of the Great Lakes. Kraken Mare, the largest body of liquid on Titan, covers somewhere around 400,000 square kilometers. For comparison, the Caspian Sea, the largest lake on Earth, covers about 371,000 square kilometers. Kraken Mare is bigger. And Kraken is not shallow. Sonar measurements from Cassini suggested depths potentially exceeding 300 meters in some areas. From orbit, radar maps of these features look like detailed coastal surveys. Inlets reaching deep into the surrounding terrain, peninsulas jutting out into the liquid, islands scattered in the offshore shallows, drainage basins feeding in from multiple directions. If you removed the labels from a Cassini radar map and handed it to a geographer, they might reach for a reference atlas before realizing something was wrong. That is the trick. That is what makes Titan so fundamentally unsettling. The geography is familiar. The processes are familiar. Evaporation, condensation, precipitation, erosion, deposition. Every one of those words applies to both Earth and Titan without modification. The machinery is identical. The ingredients are alien, and that combination, familiar process, alien substance, is more disorienting than pure strangeness would be. A planet of solid iron is alien. A planet of liquid metal is alien. But a planet where it rains, where rivers flow, where seas lap against coastlines that look like coastlines you've seen on maps, and all of it made of methane instead of water, that crosses a line from alien into something harder to name. Methane rain on Titan doesn't fall the way rain falls here. The gravity on Titan is about 14% of Earth's, less than a sixth as strong. Combined with the dense atmosphere, which slows falling objects substantially, raindrops on Titan would behave unlike anything you've seen in nature. Models suggest individual drops could grow to a centimeter or more in diameter before their weight overcomes atmospheric drag, much larger than terrestrial raindrops, which break apart above about 6 millimeters. And they would fall slowly, drifting down through the haze with a kind of lazy, indifferent momentum, like slow-motion footage of water drops in a lab. If you were standing in a Titan rainstorm, assuming the suit protecting you from the cold and the chemistry was working perfectly, you might almost miss the rain at first. Large, slow drops arriving without the hiss and roar of a terrestrial downpour. Quiet, deliberate. Then one would land on your glove. Methane is a solvent. It is not as aggressive as acetone or the stronger industrial solvents, but it dissolves organic compounds with patient efficiency. Many plastics and rubbers swell or degrade in prolonged contact with liquid methane. The seals in a spacesuit, the gaskets, the flexible sections at the joints, if any of those materials were incompatible with methane chemistry, the rain would not just soak you, it would work its way into the joints. It would begin attacking the polymer chains in the seal material, slowly, quietly. In a pressure suit operating at negative 179 degrees, where any seal failure means instant death, quiet and slow is not reassuring. The ground Huygens landed on was another revelation. The probe hit the surface and did not bounce, did not slide. It sank very slightly, a millimeter or two, then settled. The deceleration data suggested a thin, firm crust sitting over something softer underneath. Scientists interpreted it as analogous to wet sand, or crème brûlée, a crisp top layer over a softer, more yielding substrate. Except the moisture saturating that substrate was not water. It was liquid hydrocarbons. The surface of Titan is, in some places, essentially a methane-soaked sandbar. The camera on Huygens captured one image from the surface, just one taken in the first few minutes after landing, before the batteries gave out and the mission ended in silence. That single image showed a flat plain scattered with rounded objects, pebbles and cobbles of varying sizes, ranging from a few centimeters to perhaps a dozen centimeters across, lying on a darker, finer substrate. They were smooth, rounded, shaped by the patient work of flowing liquid, the constant abrasion of grains against grain, the way rivers and streams polish everything they carry over long enough timescales. They looked exactly like river rocks on a gravel bar in Arizona, or the stony bed of a stream in the Scottish Highlands. One of the imaging scientists working on the Huygens team, commenting on that photograph in the weeks after the landing, said the scene could have been mistaken for a dry riverbed on Earth. Not a vaguely similar landscape, a dry riverbed, that precise, that familiar. Except those pebbles were made of water ice. At negative 179 degrees Celsius, water ice is not the soft, slippery substance you encounter on a winter sidewalk. It is hard as granite. Mechanically, structurally, it behaves like rock, because at those temperatures, the thermal energy that makes ice plastic and slippery under pressure is simply not present. Those river rocks are made of frozen water, harder than most terrestrial stone, shaped not by liquid water, but by rivers of liquid methane that had long since receded or shifted course. This is what Titan does. It hands you something recognizable, a riverbed, a coastline, a rainstorm, a dune field. Then, when you reach out to touch it, reveals what it is actually made of. And the revelation is always worse than ignorance would have been. Consider the dunes. Cassini's radar instruments, during repeated flybys of Titan between 2004 and 2017, mapped vast fields of linear sand dunes in the Moon's equatorial regions. These dunes stretch for hundreds of kilometers in long parallel formations, separated by valleys of exposed bedrock or organic substrate. Their dimensions, height, spacing, shape, overall organization are nearly identical to linear dunes in the Sahara Desert, the Namib Desert, and other great terrestrial ergs. Same scale, same spacing, same sinuous, elegant shapes. From a radar topography map, the equatorial dune fields of Titan and the Rub al-Khali Desert of Saudi Arabia are almost indistinguishable in form. The sand forming those dunes is not silica. It is not any mineral found on Earth's beaches. The grains are made of tholins, the same complex hydrocarbon molecules raining down from the smog layer above. These particles form in the upper atmosphere, grow as they accumulate charge and chemical bonds, eventually become heavy enough to fall, and settle onto the surface after a journey through 100 kilometers of orange haze. Titan's deserts are built from atmospheric chemistry, grain by grain, over millions of years. The sand is organic. The dunes are organic. If you scooped up a handful and tried to run it through your fingers, you'd be holding molecules that would be acutely toxic to human tissue in any sufficient concentration. There is a detail about those dunes that deserves more attention than it typically gets. They move in the wrong direction. Titan's prevailing winds near the equator blow generally from east to west, consistent with the moon's slow 16-day rotation and the dynamics of its thick atmosphere. The dunes, however, are oriented west to east. They point in the direction against the prevailing wind. For years after Cassini first mapped them, this was an open puzzle. The leading explanation, supported by atmospheric modeling and surface data, is that Titan experiences occasional, powerful, equatorial methane storms, rare events far more intense than the ordinary drizzle, that generate violent surface winds blowing opposite to the prevailing direction. These storms may happen infrequently, on timescales of decades or centuries, but when they come, they are strong enough to overwhelm the everyday wind and push the dunes the wrong way in a matter of hours. The ordinary weather builds the dunes over millions of years. The storms reshape them in an afternoon. Titan's deserts are not just alien in composition, they are sculpted by tantrums. And beneath all of it, something stranger still. Between 2006 and 2012, Cassini performed a series of precise gravitational measurements of Titan during repeated close flybys. By tracking the spacecraft's trajectory with extraordinary precision, measuring changes in its speed down to fractions of a millimeter per second using radio Doppler techniques, scientists could map variations in Titan's gravitational field that revealed something about the interior structure of the moon. The data told a story nobody was fully expecting. Titan's crust, the rigid outer layer of ice and rock and organic material that you would stand on, does not sit directly on solid mantle rock. It sits on ice, and below that ice, models strongly suggest there is a global ocean of liquid water, not on the surface, not accessible, buried under an ice shell estimated to be somewhere between 50 and 100 kilometers thick, sitting in permanent darkness, cut off from the surface by a geological thickness of frozen material, possibly mixed with ammonia, which would act as antifreeze, keeping it liquid at temperatures far below water's normal freezing point. Titan has two faces. The one on top, the one Huygens photographed, the one Cassini mapped, is a frozen methane world dressed in Earth's clothing. The one below is a hidden water world, a subterranean ocean of liquid, sitting in the dark under 100 kilometers of ice, where no light from the distant sun has ever reached, where no human instrument has ever come close to touching. We know it is probably there. We cannot see it. We cannot reach it. We can barely detect it. Through the subtle gravitational signatures it imprints on spacecraft trajectories measured from thousands of kilometers away. That subsurface ocean raises questions that keep astrobiologists awake at unreasonable hours. If there is liquid water beneath Titan's crust, and the evidence that there is grows stronger with each refined analysis of the Cassini data, and if that ocean is in contact with a rocky silicate core beneath it, then there is a genuine possibility of hydrothermal activity. Hot water reacting with silicate rock is one of the most consistently productive recipes for chemistry and possibly biology that we know of anywhere. It is the same chemistry that powers the ecosystems clustered around hydrothermal vents at the bottom of Earth's deep oceans. Those vent ecosystems support entire food webs built on chemosynthesis rather than photosynthesis, thriving in complete darkness, at pressures that would crush a human body, fed entirely by the energy of chemical reactions between water and rock. If Titan's subsurface ocean has a rocky floor that is geothermally active, the same process might be happening right now. A kilometers-thick ocean of water and ammonia sitting in perfect darkness under unimaginable pressure, with heat and chemistry bubbling up from below, completely invisible from orbit, completely inaccessible to any instrument we currently have or have planned. The question of whether anything lives in that ocean, or ever has, is one that current technology cannot answer. But the surface has its own strange candidacy. In 2015, a team of researchers at Cornell University, led by James Stevenson, Jonathan Lunine, and Paulette Clancy, published a paper modeling what a cell membrane might look like if it had to function in liquid methane rather than liquid water. The engineering problem is fundamental. Life on Earth uses lipid bilayers, thin sheets of fatty molecules that spontaneously self-organize in water into closed, flexible membranes that can separate an interior chemistry from the exterior environment. That chemistry works in water. It does not work in liquid methane. The physical principles are different. The temperature is more than 200 degrees lower. The molecules that form lipid bilayers in water do not self-organize in the same way in methane, because methane interacts with them differently. The Cornell team started from scratch. They looked at the thermodynamics of nitrogen-containing organic molecules, molecules that are actually abundant on Titan's surface, and modeled how those molecules might behave in liquid methane at Titan temperatures. They found a class of theoretical membranes they called azotosomes, from the French word for nitrogen, that could in principle form stable, flexible, closed structures in liquid methane, structures that would behave functionally like cell membranes, structures that could, in principle, form a boundary between inside and outside. Nobody has found an azotosome in nature. Nobody has demonstrated that they exist outside a computational model. But the fact that the chemistry is theoretically viable, that the physics of nitrogen compounds in cold methane does not forbid self-organizing membranes, means something. It means Titan is not just a geological curiosity. It might be capable of hosting not merely life, but a completely different kind of life, a form of biology built on entirely different chemistry, operating at temperatures where terrestrial biochemistry simply cannot function. One that doesn't need water, doesn't need warmth, doesn't need anything that terrestrial life considers non-negotiable. That thought is either the most thrilling thing you have encountered this week or the most disturbing one, depending entirely on your tolerance for the genuinely alien. Pause on what it would actually mean if that chemistry works. If azotosomes are not just theoretical constructs, but physically real structures assembling themselves right now in the methane seas of Ligeia Mare, it would mean that life, or something functionally indistinguishable from the precursors of life, found not one solution to the problem of self-organization, but two. It would mean that the particular chemical architecture of terrestrial life, the water-lipid-protein paradigm that every living thing on Earth shares, is not the only possible answer to the question of how chemistry builds a boundary and starts calling itself alive. Earth biology is water-centric. It assumes liquid water as the solvent, moderate temperatures as the operating range, carbon and oxygen and hydrogen and nitrogen in specific configurations as the working materials. The entire history of astrobiology, until very recently, assumed that life elsewhere would be broadly similar, because it had to be, because those were the conditions life needed. Titan challenges that assumption not from the direction of philosophy, but from the direction of chemistry. The math, according to the Cornell team, actually works. Nitrogen compounds in liquid methane at cryogenic temperatures do not spontaneously become impossible to organize. They just organize differently, into something stranger and colder and utterly unlike anything in your body, but potentially functional. And function, the ability to maintain an interior chemistry, to separate self from environment, to resist entropy locally at the cost of entropy globally, is arguably what life is, stripped of all its other properties. Titan might be doing that, quietly, in its methane lakes, right now, without knowing what it is. There is more. In 2010, two separate research groups working independently, using different analytical methods on the same Cassini data, reported anomalies in Titan's lower atmosphere that have never been satisfactorily explained by non-biological chemistry. The first study, led by Roger Clark at the U.S. Geological Survey, found that hydrogen molecules flowing into Titan's upper atmosphere from the solar wind appeared to be disappearing near the surface. They were going down in concentrations detectable by Cassini's spectrometers. They were not coming back up. Something at or near the surface was consuming hydrogen, absorbing it, removing it from the atmospheric cycle in a way that standard abiotic chemistry could not fully account for. The second study, led by Daryl Strobel at Johns Hopkins University, found a puzzling deficit of acetylene near Titan's surface. Acetylene forms abundantly in Titan's upper atmosphere through photochemical reactions. Models predicted it should be accumulating on the surface, building up over geological time. It wasn't. Something was removing it faster than photochemistry could produce it. Before Cassini arrived at Saturn, the astrobiologist Chris McKay, one of the preeminent researchers in the field of non-terrestrial life, had published a theoretical paper. In it, he proposed a thought experiment. If methanogenic life existed on Titan's surface, What would be its metabolic signature? What would it consume and produce that might be detectable by orbital instruments? His answer: such life would breathe hydrogen and consume acetylene as an energy source, producing methane as a metabolic byproduct. The missing hydrogen and the missing acetylene, discovered years after McKay's prediction by two independent research teams using two different instruments, fit that prediction. Not approximately. Specifically. Nobody claimed this was proof of life. Non-biological explanations were proposed, and most scientists favor abiotic explanations for both observations. But two independent datasets gathered years after a specific biological prediction was published, both pointing in the predicted direction. That is the kind of convergence that makes scientists extraordinarily careful and extraordinarily curious at the same time. The scientific rule for extraordinary claims demands extraordinary evidence. This is not extraordinary evidence, but it is extraordinary coincidence. And extraordinary coincidences in science have a habit of eventually resolving into one of two things: a mundane explanation that closes the question, or a discovery that opens everything. What makes all of this worse, or more compelling, depending on your perspective, is the silence. Titan has all of this complexity. Rain and rivers and seas and hidden oceans and organic dunes and anomalous atmospheric chemistry and theoretical cell membranes and missing hydrogen. It has more going on geologically and chemically than most of the solid bodies in the solar system. And we have almost no data from the surface. Huygens survived for 72 minutes after landing. One photograph, a handful of temperature and pressure and chemistry measurements, a few minutes of wind noise, then silence. Everything else we know about Titan was gathered from orbit, from the radar and infrared spectrometers and mass spectrometers and gravity mapping instruments aboard Cassini during 13 years of flybys. We mapped Titan the way you would map an unfamiliar city by flying over it at night in an aircraft with a single flashlight pointed out the window. We saw shapes. We inferred materials. We built models. We argued about the models. But we have physically touched the surface of Titan exactly once, in one location, for barely over an hour. In planetary science terms, that is the equivalent of sampling the Pacific Ocean by briefly dipping a fingertip into the water off the coast of Hawaii and drawing conclusions about everything that lives there. Think about what that means in practical terms. Mars, a planet we have explored more intensively than any other body beyond Earth, has hosted over a dozen successful surface missions since 1976. Rovers have driven a total of tens of kilometers. Drill samples have been extracted from multiple locations. The Ingenuity helicopter has made dozens of flights. And yet Mars scientists still argue about fundamental questions regarding the planet's past habitability, the history of its water, the nature of its chemistry. Titan, a world arguably more chemically complex than Mars, has had one lander. One for 72 minutes. On a world roughly 4 times the size of the Moon, with a surface area of over 80 million square kilometers, we have a single data point, one patch of organic-soaked gravel, photographed once by a probe on borrowed time. NASA is going back. A mission called Dragonfly, a nuclear-powered rotorcraft the size of a large car, carrying a suite of scientific instruments capable of autonomous navigation and powered by a radioisotope thermoelectric generator running on decaying plutonium-238, is currently planned for launch in 2028, with arrival at Titan tentatively scheduled for the mid-2030s. It will not land in one place and wait the way Huygens did. It will fly. Titan's combination of thick atmosphere and low gravity makes it one of the most aerodynamically favorable environments in the solar system for powered flight. The dense air provides abundant lift, and the weak gravity means you need relatively little of it. Dragonfly will use its 8 rotors to hop across the surface, covering 8 to 10 kilometers per flight, exploring dozens of distinct geological sites across years of operations. The mission plan calls for beginning in the equatorial dune fields and working progressively toward Selk Crater, an impact structure approximately 80 kilometers across, where scientific models suggest that the energy of the original impact was sufficient to briefly melt the subsurface ice and create a transient pool of liquid water on the surface. For a period following the impact, possibly hundreds to thousands of years, liquid water would have existed in that crater, mixing with the organic material raining down from Titan's atmosphere above. For a brief geological moment, both of Titan's potential chemistries, the water-based underground chemistry and the methane-based surface chemistry, would have coexisted in the same location. The mixing zone at Cell Crater is the place where, if you wanted to find evidence of complex prebiotic chemistry, you would look. The engineering alone is a quiet kind of madness. Dragonfly's rotors have to generate lift in an atmosphere 4 times denser than Earth's, which helps, but at temperatures where most lubricants behave differently, where electronic components face failure modes that have never been tested in real-world conditions, where the power source is a chunk of decaying radioactive material that generates heat and electrical current regardless of whether anything else aboard is functioning. The probe will fly for roughly 30 minutes per hop, land, recharge its batteries from the RTG over the following hours or days, run its instruments, analyzing soil samples with an onboard mass spectrometer capable of identifying complex organic molecules, scanning the subsurface with a seismometer, measuring the local gamma-ray spectrum to determine elemental composition of the surface material, and then fly again. Each hop will be navigated largely autonomously using visual odometry and inertial guidance, because the 80-minute one-way communication delay between Earth and Saturn means that real-time control is impossible. Every landing decision, every navigation choice will be made by software running on processors inside a titanium shell at the bottom of an alien sky. Dragonfly is navigating with maps drawn by a spacecraft that has been dead since 2017, when Cassini was deliberately guided into Saturn's atmosphere, its mission concluded, its fuel exhausted, and destroyed. Dragonfly follows in the path of a ghost. What Dragonfly finds, or doesn't find, at Cell Crater could redefine the boundary conditions for life, not because finding complex organics there would prove biology. It would not. But if the chemistry in that crater shows signs of organization, of preferential molecular handedness, of complexity far beyond what random thermodynamics should produce, if it shows, in short, signs of something trying to happen, then Titan stops being a curiosity and becomes a data point. We have one example of a world where chemistry became biology, Earth. If we find a second place where chemistry was moving in that direction, even if it never crossed the line, even if Titan's life, if it exists, is still just chemistry trying and failing, 2 examples is not twice as interesting as 1. 2 examples is a pattern. A pattern suggests a universe where this happens, where chemistry slides toward biology given enough complexity and time and the right conditions. 1 example is a fluke. 2 examples is a law. Until then, Titan waits. It keeps raining methane into dark rivers that carve their way through plains of organic sediment, emptying into seas no human eye has ever directly seen. It keeps rotating under its orange sky, slow and cold and indifferent, completing 1 day every 16 Earth days, 1 year every 29 Earth years. It keeps hiding an ocean of liquid water beneath 100 kilometers of ice, an ocean that may be older than Earth's oceans, that may have been sitting in the dark since before complex life appeared on our planet. It keeps wearing Earth's face over a body built from poison and cold and strangeness. And it keeps asking a question that we cannot yet answer. Every other genuinely hostile environment in the solar system has the basic courtesy to announce itself. Venus is a furnace. From orbit, from the ground, from every measurement we have ever taken, Venus shouts what it is. 465 degrees Celsius at the surface, atmospheric pressure 90 times Earth's, clouds of concentrated sulfuric acid cycling through an atmosphere dominated by carbon dioxide. It gives you no comfortable illusions. Jupiter is a wall of radiation and crushing pressure, a gas giant with no surface to stand on, a radiation environment so intense that it destroys spacecraft electronics in hours. They announce what they are. They do not deceive. Titan is different. Titan looks like a place you could land, a place you could walk. A place with shores and skies and weather and geology and the general visual vocabulary of habitability. It invites you in. It shows you the coastlines and the rainstorms and the river valleys and the dunes. It shows you something that looks, at first glance and second glance and third glance, like home. And the longer you look, the more you realize that everything familiar about it is built from something fundamentally, irrevocably wrong. The rivers run with methane. The rain is a solvent. The ground is soaked with hydrocarbons. The air is a chemical factory producing tholins. The sunlight barely reaches the surface. And beneath everything you can see, buried under a geological thickness of ice, there is an ocean of cold water that may or may not be empty. Titan doesn't scare you with fire and pressure and radiation. Titan scares you with familiarity. It is a mirror that shows you Earth, and then, very slowly, very quietly, shows you what the reflection is actually made of. That is what makes it the most unsettling object in the solar system. Not the cold, not the methane, not the toxic haze or the hidden ocean or the alien chemistry of its theoretical membranes. It is the resemblance. It is the fact that Titan appears to have studied Earth's homework, copied the format with extraordinary precision, and filled in every answer with something from a completely different language. We look at Titan and see ourselves reflected back. Coastlines, weather, a thick sky, seasons, the geography of a habitable world. And the reflection is wrong in ways that take time to notice and longer to fully understand. A world that feels familiar but isn't. A mirror that doesn't quite match. The kind of wrongness that you feel before you can name it. If that doesn't unsettle you, spend a quiet minute looking at Huygens' single-surface photograph. River rocks on a flat plain, a hazy horizon, light that could be late afternoon anywhere in the temperate zones of Earth. It could be a dry wash in the Mojave. It could be a gravel bar beside a Scottish burn. It could be anywhere you've walked, anywhere you've stood, anywhere you've felt the ground under your feet and the sky above you and thought, this is a place. This is real. This is home. It is none of those things. It is the surface of a moon orbiting Saturn 1.2 billion kilometers from the sun at negative 179 degrees Celsius, soaked in liquid hydrocarbons under an orange sky that hasn't been clear since the solar system was young. And in the mid-2030s, a small helicopter is going to fly through that haze. It's going to land on those river rocks, or ones very much like them, run its instruments, lift off again, and fly to the next site, and the next. And the next. It is going to tell us, at last, what Titan has been hiding under that borrowed face for 4.5 billion years. There are two possible answers. In one, Dragonfly finds complex organics at Silk Crater that are interesting, but ultimately explainable. Products of abiotic chemistry, atmospheric photochemistry, impact-generated reactions, sophisticated but lifeless. In that answer, Titan is a chemical masterpiece and nothing more. A world that assembled all the ingredients and never baked the bread. A demonstration of how far chemistry can go without becoming biology. That answer would still be scientifically revolutionary. It would teach us about the upper limits of prebiotic chemistry. It would refine our models of where life can and cannot arise. It would be extraordinary. And in the other answer, the answer that nobody dares say out loud in too much detail because the implications are too large and the evidence is still too thin, Dragonfly finds something that doesn't fit. A molecular handedness. A polymer too regular to be random. A pattern in the chemistry of that crater soil that resists every abiotic explanation. A second genesis. A second completely independent origin of organized matter that we would have to call, by any reasonable definition, alive. If that happens, if Dragonfly sends back data that forces us to conclude that Titan figured out biology on its own, with different ingredients in different conditions, without any connection to the only life we have ever known, then every assumption we have ever made about our place in the universe changes permanently, irreversibly. If life arose independently twice in the same solar system, it almost certainly arose everywhere conditions allowed. And conditions, as Titan demonstrates, are far broader than we thought. Whether the answer is the most exciting discovery in the history of science, or the most profound confirmation that the universe can be both beautiful and completely indifferent, I genuinely do not know. Neither does anyone else. That is exactly why we are going. I hope you enjoyed the video. If you did, please consider leaving a like. It helps more than you might think, and it tells the algorithm that this kind of careful, science-driven content is worth surfacing to more people. If you want to be here when Dragonfly launches, when it arrives, and when the data starts coming back, subscribe so you don't miss it. I'll see you next time.